Good afternoon, everyone. I'm Mikhail. I work at the YADRO company. I'll tell you how we use integrity block in Linux block integrity. It started from storage system we make. It has got the mechanism of data integrity, data protection, and we should protect ourselves from stealth corruption and this raid. So its data is not just inconsistent, but we should pinpoint the reason of inconsistency. We should store metadata about data, such accounts and so on, but not externally, because it's a distributed, dedicated, right? So we need dedicated distributed storage. We need something simple for this task. Most simple thing which came across us, there are hard disks with extended sector. Let's extend it to 16 byte more and write down metadata there, checksum, and everything will be all right. We'll launch format unit command on our 12 terabyte disks. It's for 16 hours, but nothing works because Linux is saying that the sector size is rather strange. It doesn't look like 4 kilobyte. It doesn't want to work with that. We look at the drivers. The driver says that this sector is not just, it should be equal 512. We can make our own driver for the disk, but who will do that? It's very difficult to support it, to put it into the kernel. Then we can just store metadata in the disk. Looks quite expedient, so we decided to search for it. 15 years ago, everything has been standardized at the stage of standard T10 protection information, which prescribes the procedure to protect. The standard says that for each sector we store 8 bytes. The format is strictly defined, and there are lots of different other words like DIF, DIX, EDP, and others which describe the way we should store this metadata, how we should transmit it by wire, not to break data and things like that. As to the simple level, we have got this data block, user data, and for each is 8 bytes, checksum, metadata, and ACTPAC, and reference tag, application meta. Sometimes it could be metadata, sometimes not. It's necessary because when this data is going through the wire, they do not change place, or if they do, we should notice. Okay, we have got 2 bytes. It's metadata user plus 4 byte, 6 byte for sector. It's cool. We can write a lot of different things using that. Actually, at the end of the day, it's a lot in the standards. So each sector could have several data blocks. Here for one sector, there are 4 blocks. It could be configured at the level of SCSI device, and it's not so very important indeed. Well, we sorted out with the disk. Everything's in the disk. In the core, it's very good support. We have to register this device as something having integrity and to link it to a profile. And then as to bio, we attach metadata to bio, add page, write metadata. Metadata could be anything, any kind. It's the implementation which is ready to main integrity. A module installs its own data set, and we write metadata in other places as well. It's very generic thing, so we can do a lot of things with that. And as for T10, it's already in the kernel. In practice, we have to format the disk. We change geometry. It's 4K sector, type 3. And what's interesting is that for type 3, it's P41, as for type 1, it's type 2. Why is that? It's just the way it is. Sometimes we need 6-byte commands, sometimes 10-byte command. We have just calculated that, and it turns out that type 3 is not existent in hard drives, so 6-byte sector will not be present there. So no type 3 support. So we'll do it for type 1, wait for another 16 hours, nothing changes. Only the size is smaller. It's type 1. TIFF block level does know it, says there are no integrities, no tags, anything as it used to be before, but smaller. But we look at the disk, yes, we do read capacity, and it says again, it reiterates that everything is in place, but nothing is working, as usual. So we try to sort it out, and we figure out, and we understand that integrity should be included, not as on the disk itself, but also at the level COSBES adapter, which should support integrity. In our case, you can see the way it is in the slide. Linux Sense data, they are in Hubbub, sees that the disk should have protection information, HBAs, reads it, inserts it, and then reads it, but it does work backwards actually. It's cool, but that's not what we need. So correspondingly, once again, we look at the driver and we see that it has got special parameter to include data integrity field as support. We include this disk, reboot the driver, launch everything, and block device says that we have got this T10 format. Tag is yet 0, but it's not so bad. So we progress, and tag size is that application tag, which tells us how the amount of bytes we could store in metadata. It's bit A2 in the control mode, page number A, and it's very straightforward command. That's how we can write it. If we refer to guess key, when you will use the energy capacity, it will be persistent. After that, we insert everything, and as we understood, so everything starts where it's supposed to start working, but nothing works. Integrity is there, tag is there, but when we try to record it in the disk, there are HBA errors. They're very informative. At least LSI and Broadcom are very keen on using those numbers. The documentation, if we look through it, will show that in one case we were reading more than we can, or writing more than we can. Something went wrong in the word. In this particular case, we were helped by the driver from vendor. We uploaded from the drive, from the HB, then we debugged this. We made an attempt. Why in upstream and in Linux it doesn't work? That attempt entailed the situation that we know that in driver and upstream cache information is not existent. When the driver was placed inside, they decided they don't need it, so they just omitted it. It's there, but it is not, sort of. So the vendor of the driver is very important too. So if we put everything together, we have to take disk with the right form, correct format, correct drive setting, correct HBA settings and HBA driver, and then we'll get the disk which supports system integrity, 2 bytes for sector we can write, and we can read and write data even. It was about SCSI SAS as to NVMe. In NVMe PI, everything is the same but slightly different. The standard, the format itself is fully taken from T10, describes the same fields. The only thing is that it's optional. The disk may not support, and consumer disks are not supporting it. It could be configured at every namespace format. You can have different formats of namespaces in the same disk. And if you wish something bizarre and strange, it might not work. There were some situations when a two-port disks, which one port is looking towards one host, the other one towards another host. There were protection bugs in the namespaces which don't have this protection, which is nonsense. Vendor couldn't explain. Maybe there was some bug which we couldn't find. In NVMe, there is another thing. They can store metadata without all those integrative things. 8-byte could be written and could be read if disk is not there. It's in no-profile core networks. In the disk, if we check out the notification of namespace, it'll look like this. Certain parts are in charge of which type of protection is just included. Below you can see different formats and protection information types, like type 3 is enabled. I show it. We need a format with 8-byte per 4 kilobytes, 8-byte metadata 4-byte format. And then this is cool. We know we can read and write this. How could we code it? How could we program it? What will be in the fields? That's what we have seen. How should we program and code it without specific hardware? It's even better on laptop, and also use run tests, different virtuals, and so on. So we need something which will make this cloud device, which will make this model of information protection. And it could be launched on anything, on very straightforward devices and hardware. So in Linux, we have got a cool thing which is called SCSI target. Typically, it's used for export this kind of fiber channel out of Linux. Outwards, there is backend and frontend, and all together it's like SCSI device. We have got this file, it's a file backend, and it has got the support emulation of this integrity metadata, and we can take it as a backend for our purposes. On the other hand, we have that loopback front end. Anything we can wrap it up as a local SCSI device, so out of file metadata, so it's SCSI device which can do the integration of the data, and it can work in any format on any hardware. It looks like this in those squares. A disk with file system, data, metadata, files, target core, TSM loop, SDB disk with metadata appears here. It works. By the way, it works in virtual as well. You can work it on laptop. It works like it looks on this picture. Though it could do better, but it works the way it can. It's okay for the development. We started making the software based on that and coding based on that. So as to integration, we should have the devices inside the virtuals which protect the information.
And we need both in-test components that will make it possible to test, and integration tests that require cluster environment, shared disks, and the lack of inner configuration in the virtual system. So we have to put those block devices there. With the first, NVMe is quite helpful. NVMe disk that make through PCI post to insert the disk into virtual. We take PCI device and we put it, but one disk can only be put in one area. Two-port disks might be quite good for us, and we might launch two virtual systems on one disk, and you have seen CRV in one disk and configure it. That will be really great, but unfortunately I haven't seen the people who would see that operation. As to SCSI, in the previous slide we had a side disk connected to HBA in the host. And we have a SCSI device which we can use the same picture as we had for laptop, but we shouldn't use the loopback device, but vhost. Then what we have then, we take a disk, we put it into iBlock target that makes the backend from any block device. Then we go to give it to the host that represents virtualized SCSI. HBA SCSI host, and in the virtual system it is used as virtual SCSI HBA, and there is a separate root, and inside the virtual machine we have one SCSI driver that can use it. So we have taken SCSI disk and put it into the virtual system, and we have protection information throughout the operation root. If you recall that starting from core 4.12, we can transfer this Malygin as it is. We can multiply the picture for 3 or 4 virtuals. So we can use one disk between 3 virtual machines. Thus we can test a cluster setup on shared disks together. And if we remember that the disk has 2 ports, as in normal CS disk, we have such situation, we have 2 hosts with a lot of virtual systems on each, and everything is in one disk. The only problem is that this wouldn't operate. All the structure is assembled, but there is no information protection. DevDex doesn't work. If you look into the driver, vhost and virtual driver metadata copied, but it doesn't work, and we looked up for the source system, and these drivers agree through the set of VG bits, one which is PDP, that should be put on both sides. Then protection of data is allowed, and they try to transfer data. Where from would we get it? And good sense prompted that virtualization system would do it instead of us. And in qemu 3.1 there is a support of that feature bit. I just collected that qemu with feature bit switched on, and vhost, virtual SCSI, vhost have found each other, and they agreed about this bit. Later, it was clear that we can transfer that bit switched on, and any virtual system would be able to install that bit, and that is an example of configuration of vhost. The problem is that we have learned that we have everything with negotiation T10. When everything stopped reading, any record of reading gave an error and said that there is a block number request. But block number request, that means that probably the size of the lock is inadequate. Logs on the host said that we have unbalanced block size, and 66 bytes are stealed from each host. If you send 80 kilobytes and this amount is stolen, we add logs to everything that we can add to. And it appeared that data disappear inside in vhost, and they are not correct. We can see this patch that was devised 1 year ago. Everything is broken in this structure for 4 kilobyte block. Instead of checking how many metadata should we have for this block device, 8 bytes by 4 kilobytes, they thought that for each sector there will be 80 bytes, and in Linux the sector is 512. We have patched it, we have collected it, everything operates. We start testing our wonderful application, and immediately nothing would work. First that we came across is error 84, logical block reference tag, check failed. Reference tag is following, so the data in the wire would not change their places while they're flowing. Probably that is good for Sun or Chkazi long ago. The idea is that for each block we write a certain sequence. In the first block that is LBR, and in the next block we write LBR, that is 1 unit. Great, according to the standard. As to good sense, for each LBA, in each block, we write the lower LBA, lower bit LBA with 4 kilobyte block. Is interesting. In Linux, the block is always 512 bytes, and everything is counted in these sectors. This looks as follows. When we have the sector of 512 bytes, we put byte data and write LBA and reference tag. When it falls to SCSI, there is the same situation. In the 4 kilobyte sector, the situation different because LBA for each block increases by 8, and ref tag should increase by 1. If we remap automatically ref tag from 512 bytes to 4 kilobytes, it is inside of Linux with a block device, and it checks that the first LBA are correct and the next by 1 unit. If that condition is observed, it will remap the block. If not, it will be left as it is, and the device will reject these blocks. So there was a bug in the soft which we had to repair. The second story was related with the fact that in virtual SCADA we couldn't write more than 128 pages of 64 kilobytes. That at first we thought, okay, that will be a great number per request, and we moved further, and then it appeared that 32 pages in NVMe is NVMe is our limit. We had to analyze it, and the reason was that the scheduler of the core, when it saw a very large BIO, more than with many signets, it split it into 2, and our favorite reference tags were separated because remapping didn't work for the 4 kilobyte disks, and nothing would operate as well. So what should be done so that it wouldn't be split? The third story was when we wrote in NVMe, all metadata should be successfully on 1 page without any exceptions, and max integrity SMS was in 1 unit, and NVMe of the core in Linux works only through the mechanism of PRP. Reading pages, I don't remember, and only through mapping of the pages it would operate, and the limits of that mechanism is that all the metadata should be on 1 page or should be merged with other data, and it should be presented successfully, and after that probably it will work. In NVMe disk, signals more than 4 kilobytes do not work. It is not written anywhere, but no one is concerned with it because in x86 the pages are of 4 kilobytes. We have OpenPower 64 kilobyte pages. Linux, everyone said that it was possible, but Linux disk try to reject reference tags again. So we divide everything by 4 kilobytes, and it will perform. Anything else? As to performance, as was mentioned earlier, the first field should always be the checksum of the block which you write in quasi-standard, that is quasi-standard that might be CRC6 or IPX sum, probably when they just analyze how to count CRC data. So the standards were supporting IP, those that support HBS, so the host is reading IP. And then it transfers HEBA, checks P and SCSI and metadisk. Everything is computed quicker, but in NVMe it doesn't work. Probably they decided that their processors are quick and you can can't RT16. In the core there is a special driver, CFC10 diff, that calculates these sums, and on one core, Power 8, it calculates at 100 megabytes per second per core, which is really a shame for the storage system. Therefore, everyone recognizes that this is a shame. So, that 86 in old times was based on PCML driver, which on vector structures, usually special schemes make it possible to compute quite quickly. Since that time, probably for a long time, no one was concerned with this problem. Everyone used Intel to calculate. Only in 412 core there was realization of vector checksum, realization of checksum for vector structures and power architecture in VBIM. So when we switched it on, it appeared that it operated well, but quite slowly. We just start FIO, and it gives 200 megabytes per second. That's really great, but not. So the problem was FIO because it parallel counted MD5 for all data. We removed checksum, and now the driver can count at the level of vector regime several megabytes per second. That is important for our task. There are two other realizations for ARM64 that appeared in 410 and 5.1 core on cryptoblock ARM. They make it possible to calculate the checksum quite quickly. And if you look at what is the outcome, everything works. On Skype, on NVMe, you can switch on T10 DIX and you can live with it. In principle, you can also use vhost and virtio SCSI. That will also work, but sometimes the operation will be strange. When we switch it on power, virtual machine will be loaded for the 20 seconds more than on this disk. There was a certain bug with firmware, power for QEM, which on the start, before loading the core, started to palpate the disk and check what is the situation with the disk, and it didn't like something, and there was a delay. And we decided to patch the firewall and to switch it off. In the core 412, there was a support of device mapper. Device mapper might not only generate checksums, but receive them from the outside, so we might have an integrated device that will take checksums, record them, and transfer to this. So we have an integrity model that also generates these checksums. What are we missing? NVMe protect the information, works, but as we have a two-port disk and a lot of namespace, it might not work. At minimum, two vendors saw how they work in different way, and we don't know what to do. As to qemu QVM, in addition to virtio host and virtio scandi, nothing works. Neither virtio block, nothing works. How to transfer the file? You can transfer it. Even virtio vhost user in SPDK also cannot protect the information, and NVMe driver also cannot protect the information. And as 10 years ago, there is no API for user space work. Because probably no one needs it. There is no file system support, and everything is really sad. So that's the situation, but you still can use it. So, any questions? No microphone, can't hear. No microphone.
Извините, у меня каверзный вопрос.
I have just a very curious question. Production. Is it in production? In the systems which are tested for production, that is included by default, and it will be here in the next version. So it now can be brought to production. No microphone.
Hello. Can I ask in English?
Yep.
Hey. I was wondering.
А микрофон поближе бы.
NVMe's, you probably have a lot of guarantees that your data is not going to get corrupted, and you have ECC and all sorts of other mechanisms implemented at the FTL to guarantee that your data is not going to rot. What is the advantages of trying to use diff there or PI or are you targeting lower grade drives only?
No. The key point in using diff is not trusting drives. Like we are trusting drives and we believe they are good, but we want to have an option to keep track of data from upper layers down to disks. So we want to protect from the case when maybe somebody by mistake corrupted data on disk, and we want to detect this scenario, right? So disk is perfect, maybe perfect, but our software, our processes may be not perfect, and we want to be able to at least detect that we have data corrupted, or maybe heal the data before they get to the customer on read. So it's protection on another layer.
So you're trying to keep a copy of the checksum and recheck later?
Actually, somehow, yeah. Actually, there is an option to like synchronize data between a disk in single stripe. So a stripe can protect drives that are blocks of data that are the same stripe, and say that this data on the disk should have another checksum or another gain count or some another property, and we believe that it's corrupted, so we have to reconstruct it.
Just one comment. I think SPDK 19 will have end-to-end APIs for it.
Oh, great.
Which was released some point earlier this year, maybe around April.
Oh, great. So last time I checked, it wasn't there, so maybe...
I'm pretty sure it's there, I just don't know when it came in.
Okay.
Good question. You should ask them. Well, I think I heard him mentioning that he didn't have support, so I was just pointing it out.
You mentioned NVMe as to the support versus drive. It doesn't exist at the market, or there is no specification for supporting SRI on the NVMe devices. There is specification. According to specification, there is a full description of how it should work. These are virtual functions and management of resources, and I even was told that NVMe CLI should manage these resources, but the programmer has never seen these disks, and no one has seen how these disks operate. There are sample engineering samples distributed among the main vendors to check. So they exist, but no one has seen them. But that will make my life easy, of course. Recently, Samsung announced some new disks, and they say that they have it there. Let's see.
Ну и не надо.